We're going to learn our final test for convergence. This is called the absolute ratio test, and it says let the infinite series a sub n be a series of non-zero terms, and suppose that if I take the n plus first term and I take the absolute value of it and put it in a ratio with the nth term, where the nth term is on the bottom, and I plug that ratio in the limit as n approaches infinity, if I get rho, that's the Greek letter rho, if I get rho for the answer, then the absolute ratio test tells me some things based on the value of rho. First of all, anytime that limit gives me a value less than 1, the series converges. And not only does it converge, it converges absolutely. Not only will the alternating series converge, but the positive counterpart converges as well. If rho is greater than 1, that series diverges. The only problem with the absolute ratio test is if rho equals 1. If we evaluate that limit as n approaches infinity of the n plus first term over the nth term, and we get rho equals 1, then we don't know what that series does. That series could converge or it could diverge. When rho equals 1, the test is inconclusive. What I have written down here in blue is this test fails. So this is not a foolproof test. That's why we have to have all the other tests. However, this is one of the most powerful and consistent convergence tests that we will see in all of our series work. By far, this is the most common test we will run. Let me say that in PMAC language. Know this test. Know the results of this test. Know what results are required for convergence. Know what results are required for divergence. Know what result gives you a failed test so that you have to go find another test. This test is useful for series that have exponential pieces or factorial pieces. If there's exponential terms, 2 to the n, 3 to the n, 4 to the n, or factorial terms, n factorial, anywhere in your nth term, think of running the absolute ratio test. This test is super powerful because it's the only test that we have that we can run on both positive series and alternating series. Now, a side note for the students that, go on Google and try to find out more information, which I think is fantastic. I don't have a problem with that at all. There's actually 2 different tests. There's the ratio test that's just for positive series. That's where the absolute value doesn't come into play. Then there's the absolute ratio test. It's called the absolute ratio test because we have the absolute value bars there. We know we're absolutely convergent if rho is less than 1. I no longer teach just the ratio test. Because for our purposes, when we start dealing with power series, we're going to use the absolute ratio test every time. So if you get online and it starts talking about the ratio test and the absolute value marks aren't there, understand that they're only dealing with positive series in that scenario. We can use this test on either. If all of our terms are positive, then it doesn't matter whether we have the absolute value marks there or not. They're not going to hurt anything being there. Positive, the absolute value of positive is positive, so it doesn't really hurt anything. So I just teach this one test. It's the absolute ratio test. It's the only ratio test we have to learn. It's the only one we'll be using. So never forget to put your absolute value bars on your nth and your n plus first term. But the biggest kicker here is this test can fail. If it fails, then we have to fall back on all the other tests that we know. Another little sidebar, this test stinks. for nth terms involving only polynomial or power terms. It fails a lot in that case. So, but you know, the limit comparison test is excellent for those kinds of series. So let's just get right to it. We know that we're going to put this into a limit with its n plus first counterpart, and we're going to use absolute value marks, and we're going to get an answer to that limit as n approaches infinity. We're going to call that answer rho. Based on the value of rho, we're going to be able to determine whether this series converges or diverges. So here's the work that I need to see. I need to see, as an AP reader, that you recognize a sub n is 2 to the n over n factorial. I also need to see, as an AP reader, that you recognize the n plus first term is that you go back to the nth term, and everywhere there was an n, you write an open parentheses. And in that open parentheses, you write n plus 1. Now, it's not apparent on this particular series why I want that done, but later on other series, you'll see why it's important that I want parentheses around everywhere you write n plus 1. Now, remember, the absolute ratio test is the n plus first term over the nth term. Your results for rho, if you swap those, are not going to be accurate. So please make sure that you put your n plus first term over your nth term. So let's do that. The limit as n approaches infinity. I just use one big absolute value mark. I don't use absolute values on the numerator and absolute values on the denominator. I just use one, and then I write my ratio. So my n plus first term over my nth term. That's how you're going to see me write it. There's a sub n plus 1 over a sub n. Now I have a compound fraction, so I'm going to do some algebra and I'm going to clean this thing up before I do anything. I'm taking the fraction on the bottom, flipping it, and multiplying straight across. That's all I did. That's just algebra. Now I'm going to do some things here and here that you need to pay special attention to, because this is something you're going to be doing often, since this is a test that you're going to run a lot. We're going to go back to Algebra 2, and we're going to recognize that that can be expanded and written as 2 to the n times 2 to the 1. When I multiply the same bases, I add the exponents. Now, we're used to going in this direction. If I gave you this and told you to write it as one exponential term, you wouldn't have any trouble coming up with that. We're used to going in that direction. I need you to get used to going in the opposite direction. We've used this sum occasionally when e to the x or something like that has shown up when we were doing differential equations. But it's something that's going to come up a whole lot for us now. And everything in the numerator there is multiplied together. Now I have 3 terms multiplied together. Now I want you to realize something about n plus 1 factorial. We're going to use the attributes of the factorial to kind of expand what's going on down there. And you'll see why, because it helps us clean up our limit. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Everybody agree with that? Here's n factorial, right? So if that's n factorial, then n plus 1 factorial is just going to have an extra additional lead factor in that multiplication. So isn't it true that n plus 1 factorial can be written as n plus 1 times n factorial? And then I'm just going to copy down this 2 to the n. Now, do you see why I did that? Look here. If I rewrite n plus 1 quantity factorial as n plus 1 times n factorial, here is some of the power of the absolute ratio test. Those terms algebraically cancel. The whole reason for expanding this term is that those two terms algebraically cancel. Now, let's just clean it up. The limit as n approaches infinity of the absolute value of 2 over n plus 1. Now, all that mess that we started with up there cleans up to, algebraically, I didn't do anything fancy, I just used algebra. It cleans up algebraically to this really, really nice fraction. I can actually evaluate this. 2 over huge is tiny, that's 0. So rho, and that's what rho looks like, some fancy p, rho is 0. Rho is less than 1. When rho is less than 1, my series converges. What test did I run? By the absolute ratio test. See the power of it? It's amazing. All right, so let's do another example. Here we have, so the test for convergence, this says test for convergence or divergence. Here is another term. Please remember to show the AP reader that you recognize that you have to find the n plus first term. Please, for me, and again, it's not highly obvious why we're putting parentheses around n plus 1 yet, but it will be. So show the n plus first term. We have the limit as n approaches infinity. Now I'll tell you something else that we usually do. Because every single time a sub n is a fraction, and every single time a sub n plus 1 is a fraction, so every single time I'm going to have a fraction over a fraction, even though it's going to be a sub n plus 1 over a sub n. And so I'm always going to take that bottom fraction, which will always be a sub n, and flip it and multiply straight across. So let's save ourselves some time. Let's write a sub n plus 1, and let's write the reciprocal of a sub n. We can automatically go there. There isn't an AP reader in the world that's not going to be able to go there with you. That's just fine. Not an issue. As a matter of fact, you'll get to the point where this will be how you write it down. You'll get to the point where this is just exactly what it will look like. You'll automatically do this expansion before you ever put it in there as well. Now, the one admonition that I would give you on this is you better be right about it every time you do it. If you need to take the extra steps algebraically so that you're absolutely certain you have everything plugged in correctly, by all means do it. Don't take shortcuts and get the wrong answer. So I'm about out of time. I'll do this really quickly. Please realize that the plus 1 inside those parentheses, even though I'm going to a power of 20, even at large input values, is not in charge of what's going on. The n to the 20th term, when that's all expanded out, is the one in charge of how fast it's growing. Those cancel. That cancels. The answer there is 2. Rho is greater than 1. This diverges.